So in example 1, they asked you to find the antiderivative or the general solution for the differential equation of dy over dx equals to 2. This is the same as asking you to find the general solution for the antiderivative, which we saw earlier, which is this form here. So we have 2. So what would be a function that if we derive it or differentiate it, it will give us 2. So one solution we can find is that, let's say 2x, if we were to differentiate 2x, it will give us, let's say 2x prime is equal to 2. This is one solution of the many solutions that we can find. Okay, so now if we want to find the general solution, which we note as g of x, so the general solution would be this function here, 2x plus a constant. And then we leave it as a constant because we want the general form. This is the general form, and this is the solution for the example 1 that was in your textbook. In reality, or graphically speaking, when we want to, let's say, illustrate this general form, we can just look at the lines. Let's say that this 2x is a line, right? 2x plus 1 will also be a line. 2x plus 2 will also be a line. So what we mean by the general formula of the antiderivative is we want to have or to find all the lines that will have the same slope, because as we know, the slope of a function is the value of its derivative if it's a line. Another form of writing g of x equal to 2x plus c, or in general f of x plus c, is that we write integral, which you might be familiar with, f of x plus, or not plus, times dx is equal to f of x plus c. This is another form of writing this g of x equal to f of x plus c. And this is the form that we'll be using throughout, let's say, integration. And this is also the y in the, as I said, this is also the y in the differential equations that we try to solve. So let's try to explain what this formula is. So f of x is the function that were differentiated. For instance, if we go back to the first example that we worked with, which would be 3x squared. So 3x squared would be the function f of x. dx here symbolizes the variable that we will be integrating. It's like if we had here, let's say 3y squared or 3z squared, we will have here d of z, and then we have f of x plus c. How we read this? We say that this is the antiderivative of f with respect to x. And we can also call the antiderivative of f with respect to x as the infinite integral. So the function integral of f of x dx is, we call, if we want to read it, we say that this is the antiderivative of f with respect to x. It's antiderivative of f, small f, with respect to x. And this antiderivative word can also be, we can also say that it's the indefinite integral of the function f. These are two names for this function here. Earlier in the video, I said that we do integration in order to undo what we did in differentiation, and also said that we are trying to find the original function that was there before we did differentiation. So now if you want to find the relationship between integration and differentiation, which you may have noticed, we can say that integration is the inverse of differentiation. Why is that? Because if we were to, let's say, integrate f prime of x dx, what we will find is that it's just f of x plus a constant. And as you can see, f prime and f, well, f prime is the derivative of f. So we can say that the integration undoes what differentiation does, and we get the original function plus a constant for the general formula. In other words, if we were to take, let's say, a function f of x dx with the integral, and we try to differentiate this function, let's say that we are trying to do d over dx. This is just the formula for differentiation. It's just like prime, it's the same. This shall give us, this will undo this, just like this, and did this, and we'll end up with f of x dx. Why? Because integration undoes what differentiation does, and differentiation also undoes what integration does. So for instance, without the dx, so if we had an integral and then we try to differentiate this integral, we'll end up with this function here. And then if we had the derivative inside the integral will undo the derivative, and then we'll end up with just the original function for f of x. So the relationship between integration and differentiation is just an inverse. One is the inverse of the other. So we can go from here, let's say that integration undoes differentiation, and differentiation also undoes integration. You can also look at the relationship between integration and differentiation as going forward or going backward. For instance, if we have the function x cubed, or let's say 4x cubed, if we were to differentiate this function, we'll end up having 12x squared, right? But if we were to go back or to integrate this function here, we'll end up with x to the fourth. So it's like going back in time to the time when this function was before differentiation of this function, and this is after the differentiation of this function. It's like having an axe of time, and then you are in the present. Let's say the present is this function here, and the future will be the differentiation, and the past is just integration. Integration is the past.